Hello and welcome everyone. I'm Balu Adsumilli. I lead the media algorithms team at YouTube. Together with Yilin, Wang, we are going to talk about video quality of user-generated content, its importance, and its assessment. First, we'll talk a bit about what UGC is, and then go into YouTube UGC dataset that we introduced a couple of years ago. We will then introduce and walk you through YouVQ, which is our new video quality metric for UGC. Right, so let's start with a bit about what UGC, user-generated content, is. At YouTube, we see a lot of video, about 500 hours of it uploaded every single minute in multiple countries, in various different languages. As you can see, a good bit of it is watched on mobile devices, and for good reason. Almost all of the videos we see are uploaded as user-generated content. Here is an example video, a sample, if you may, of a UGC video. These videos vary a lot in video content and quality, which is challenging in its own right for quality assessment purposes. Primarily, these are artifact-ridden. They're taken with shaky cam, in low light, usually people taking videos of their pets in their basements. These are heavily compressed. But what we have observed here is that, the content of the video and the emotional connection that the user has with that content are given more weightage than the quality of the video or the narrative itself. Now, video quality traditionally is measured in two different ways. One is subjective testing, where a bunch of opinions are collected and averaged to form mean opinion score, or MOS. Usually this is quite accurate, but it is also very time-taking and an expensive process. Right? And then there are objective metrics. These are either reference-based or non-reference-based. The reference-based ones assume that a pristine quality of the reference is available, and they provide an estimate of how far the reference is from the distorted version. And then the no-reference ones are more artifact-centric. The more interesting question here is, are any of them good for UGC? And actually, in practice, we found that these are not very reliable, specifically for UGC, for two good reasons. One is that many existing metrics only investigate low-level signals. Even PSNR, for example, mainly focuses on pixel differences. And that's not so valuable. As you can see here, when the left image has higher pixel difference compared to the original than the right one. But visually, though, the left one looks much better. Secondly, there's an increasing requirement for reliable no-reference metrics. In multiple different applications, for example, live streaming, where we do not have access to the original streams, or it's very difficult to perfectly match frames between the target and the reference streams, a no-reference metric is really valuable. And then the quality of the original becomes an important factor in UGC quality assessment. Since we see a lot of non-pristine originals, like this one, for example, the two videos, the one on the left is the uploaded version, and the one on the right is the transcoded version. They look visually very similar, but the reference-based metrics say that the transcoded version has lower quality, which is not very meaningful. So the fundamental question is, will we need to rethink video quality metrics in presence of non-pristine originals? And I think the answer is yes. It first starts with looking at the content itself and having a taxonomy for UGC. The data set needs to be distributed widely across multiple content types, complexities, resolutions, etc. It needs to be universally accessible and have ground truth data associated with it. Right? Currently, there are only very, very few number of data sets which are small in size and also don't necessarily focus on UGC. So in 2019, the media algorithms team introduced this YouTube large UGC dataset, which is approximately 1,500 videos sourced from 1.5 million UGC uploads. All of these are original uploads without any processing applied to it, and they're provided in multiple resolutions and frame rates. We did a bunch of crowdsourcing as well to collect MOS and DMOS and provide the ground truth data. There's also 600 plus content labels available for the entire set. Our hope here is that the dataset could encourage and inspire more work on UGC compression and UGC quality assessment. So we also had a couple of insights when we collected all the ground truth data for the dataset. And what we have observed is that the UGC perceptual quality related factors could be broadly categorized into three categories: video content, distortions, and video compression related. You can see examples of what low quality and high quality look like in each of these categories. For example, a video with no meaningful content commonly won't get high quality score, right? But the categorization is also done in terms of where the distortions might occur. For example, be it in the post-production phase or in the compression or transmission phase. Another insight here we found is that the complexity around UGC quality evaluation, right? Human evaluators go through a lot of internal digesting of information. They consider the blurred texture of grass in the background, heavily compressed text in the foreground, in this particular example of a gaming video. But they also know that this is a strategy game and the content is interesting for them. They would be looking at region of interest, for example, spatially isolated regions of interest, and would be taking a lot of other aspects when they consider the UGC quality score. Can we scale that? Can we come up with an automated way of generating a score that considers all these aspects? So the main motivation for our work is whether we can build a system to simulate human evaluation, which means analyzing UGC quality from all of these multiple aspects and telling us not just a score, a number, but also the rationale behind it, folding in all the interpretable indicators as to what is really happening, either with content or compression. So clearly, there is a need for a UGC-based metric. We've just discussed the motivation there. What would be the requirements here? Well, first, it should comprehensively map to MOS scores really precisely and accurately. And it should fold in all these aspects, all the nuances that human evaluators go through for evaluating UGC. Secondly, it should work well with no reference cases as well as with reference-based cases. And so with these two in mind, we developed something called YouVQ. And my colleague Yilin will introduce us and walk us through it from now. Thank you.
Thanks, Balu. Hi, everyone. My name is Yilin Wang, also from YouTube Media Algorithm team. For the rest of the talk, I'd like to introduce our new video quality assessment framework, YouVQ. I will start with a brief discussion about limitations of existing approaches, and then introduce YouVQ model design and its performance. To evaluate video quality, a classical way is to design sophisticated features and then map those features to the quality score. However, designing useful handcrafted feature is difficult and time-consuming, even for domain experts. Also, most existing handcrafted features were summarized from limited samples, which may not perform well on broader UGC cases. In contrast, the machine learning approach becomes more and more popular in UGC video quality assessment, or called UGC VQA, because it is able to automatically learn features from large-scale samples. As the graph shown here, a straightforward way is directly training a model from scratch on existing UGC quality dataset. However, that may not be the best way. For the machine learning approach, the most important thing is the training data. So let's take a look at available UGC dataset with labels. Actually, the sizes of existing UGC quality datasets are still very small compared to the dataset used in non-quality related domain, like ImageNet and YT-UGC. They usually contain millions of samples. Intuitively, the more data for training, the better model we can get. So transfer learning has been widely applied in UGC VQA. This graph shows how transfer learning works. We select a backbone model pre-trained on non-quality related dataset, and then fine-tune the model on UGC quality dataset to get the quality score. This is the standard transfer learning framework that has been used in many machine learning-based VQA models. However, we think directly using a non-quality related backbone is still not optimal, as not all backbone outputs are equally relevant to the UGC quality. As the example shown here, from objective recognition perspective, there is a human in both images. So the backbone model pre-trained on objective recognition dataset tend to be less sensitive to the difference between those two images. However, from the video perceptual quality perspective, we want the model to be sensitive to the artifacts in the right image. Of course, fine-tune on UGC quality dataset could increase the model sensitivity on visual artifacts. But due to the limited size of existing dataset, the model may not be able to learn sufficient quality-related features. To solve this problem, we introduced an intermediate retraining step. Instead of directly using the embeddings from the pre-trained backbone, we retrain the backbone on another large-scale quality-related dataset. For instance, we can add synthetic distortions like Gaussian noise and Gaussian blur on the original, and then train the model to distinguish the original from distorted versions by self-supervised learning. This self-supervised learning approach allows the model to learn quality-related features from a large number of real data, no longer restricted by subjective MOS data. We compared directly transfer learning and the one with quality-related retraining. This table shows the MOS correlation on YT-UGC dataset. We can see no matter using frozen or trainable weights, the quality-related retraining step is able to significantly improve the MOS correlation. Previously, we have discussed that there are multiple factors related to UGC quality. So in practice, we proposed to retrain multiple subnetworks. Each subnetwork focuses one quality aspect. Here is a complete framework of YouVQ. Our model includes 3 subnetworks that extract quality-related features. They provide high-level quality indicators, including the content label, distortion types, and compression level. The extracted features are then concatenated by an aggregation net to predict the quality scores for more quantitative analysis. This work has been accepted by CVPR this year. Without getting into too much details, here I summarize the innovations of YouVQ model. So besides the self-supervised learning and comprehensive feature, another important benefit of YouVQ is that for some subnetworks, the input frames are split into small patches and feed into these subnetworks without downscaling. In this way, YouVQ model can work on native resolutions and sensitive to local details. This is how we build the YouVQ framework. Now let's talk about its performance. In following slides, I will discuss the model accuracy and generalizability, and use some examples to show how YouVQ can help people understanding quality issues. This table shows the correlation with YT-UGC MOS when using different YouVQ features. First, we can see each individual features by themselves achieve reasonable correlations, which means all those features are quality related. Also, when combining those features, the correlations got significantly improved. That implies those features are complementary to each other. So when combining all 3 features, YouVQ achieved the highest correlation. Compared with other existing no-reference quality metric, YouVQ has significantly higher correlations on YT-UGC dataset. And when directly applying the model on another UGC dataset, the COVID-1K without retraining, YouVQ also performs much better than other metrics, which demonstrate good generalizability. YouVQ can also be used as a reference metric by running YouVQ on both target and reference videos, and then taking their difference. Here we evaluate its performance on YT-UGC DMOS dataset. Again, YouVQ achieves much higher correlation than all other metrics, which shows good sensitivity to video compression. Now we can see the single quality score provided by YouVQ has good accuracy and generalizability. Besides a single score, YouVQ can also help us reasoning through quality assessment. Thanks to the comprehensive subnetworks, YouVQ can provide high-level quality indicators to help people understand the quality issue. As we can see here, all three subnetworks provide reasonable accuracy. For example, the distortion net is evaluated on the candid 10K dataset with distortion classification accuracy of 0.97. And this subnetwork outputs the major distortion types detected from the video, along with their probabilities. YouVQ also can provide patch-based feedback to locate quality issues. As the highlighted region in this example, at the beginning, the quality is okay, but then the text region shows heavy compression artifacts. Such sudden quality change can also be caught by YouVQ metric. Now let's use the earlier example to show how YouVQ works in practice. Given this video, the YouVQ will generate a comprehensive quality report, including content-wise, it is a strategic video game. It has some distortions like Gaussian blur and pixelate, and it has a medium-high compression level. Looking at the quality predicted by the individual features, we found that the content quality is good, but the compression and distortion quality are low. So when combining all three features, the overall quality is medium low. We can see these findings match the rationale of human experts, which means YouVQ can help us reasoning through the quality assessment besides a single predicted score. To summarize the contribution of the YouVQ framework, it is more than a score and brings new insights to interpret UGC video perceptual quality. It provides a consistent view of quality for both no-reference and reference cases, and achieves the state-of-the-art accuracy on UGC video quality assessment. More details can be found in our CVPR paper, or YT-UGC videos and their MOS, DMOS data are available on our public website. That concludes today's talk about the YouVQ framework. Thanks for your attention.
Hey, and we're back for the Q&A, and I have with me Balu and Yilin from YouTube. Hey, guys.
Hey.
Yeah, nice to meet you. Let's get right into it. I think there's some good questions coming in already. So the first is kind of I guess a softball. It's more of a statement of disbelief. Did I understand that correctly? The UGC training dataset is openly available?
Yes, it is. It is a public dataset. You can go to media.with-youtube.com and download it right now, with all the information on subjective MOS scores and ground truth and labels and everything.
Awesome. So one question here is, how do you think about quality for live streams with the problems of lags and resolution changes happening on the fly? And does this require any changes to the methodology described with YouVQ?
Yeah, I think it does. The way we think about live streams is slightly different. People are a little bit more forgiving for live streams, and the errors that last on a per frame basis, are behind in the memory queue when people are watching live streams. So they're a little bit more forgiving. I also think that we'll need something that is purely no reference, because there is no good way for people to compare. Especially when it comes to live streams, right? But there's also, like, talking about UVQ methodologies, you need like something that is much faster, not necessarily real time, but like something that approximates the accuracy of a real time. and at least give you like the data that is more relevant for the perception of users, like how good it is, rather than how good it is compared to the original. You know what I mean? So that's the perception as it requires. And we've been trying YouVQ for live, which maybe Yilin can get into. So please feel free to add Yilin. But in general, I think YouVQ methodologies are like, it could be pretty straightforward, applicable, but the no reference version is the one that gets applied.
All right. Next one here is another quick one, I think. It's how often do you have to retrain the data set?
Yeah, maybe I can take that question. So,
Sure.
so our module has mainly two parts. One is training the subnetworks to extract quality-related features. And that part is based on self-supervised learning and trained on non-quality related dataset. So that part could be reused. And the model is fine-tuned on like a YT-UGC dataset or other quality-related dataset. And if we have specific application, then we can collect data, build a small set, and fine-tune on that set. Yeah, that's our current pipeline.
Got it. Okay, this one comes from the chat as well. Sometimes we apply ROI-based filtering on videos. For non-ROI areas, the quality will be relatively worse, and for ROI areas, the quality will be relatively better. Question is, will YouVQ have different scoring weights for ROI and non-ROI areas?
Yeah, I can start with that, and then maybe Yilin can pitch in. I do not think they will have different weights, but the consideration for ROI, if it has been predefined, will show up in the content category of YouVQ. As we mentioned, there's three different categories, right? The distortion net, the content net, and the compression net. You should see changes in the content net side of things when ROI is clearly specified. But in general, it takes into account, because it is not just an image metric, it's a video metric. In general, it takes into account like what the importance-based regions are. In the gaming example that we just saw, there are areas that are like specifically for text or for texture or the gameplay itself that are given higher ratings, especially on the CT side of things. So.
Yeah, great. So our module does not explicitly use ROI or CNC map to reweight the importance of different region, but those information may be already learned within our extracted feature.
Okay. So a couple other quick ones here. One is, are you planning to make YouVQ publicly available?
That's a good question. Yes, the intent is to make it publicly available. We are still going through the internal process here with getting the legal team on board and the PR team on board with that. But the intent eventually is to make it public and available for everyone to use.
Awesome. Okay, this is similar to what we asked last time, which is with AVQT. Can YouVQ work on encoding at 15 FPS with the original source at 30? So basically, differing frame rates, how does it work? Or does it work?
Yes, absolutely it does. And we have tried that. We're still in the process of pressure testing some of these use cases, but it is giving us better results than any of the other metrics that we've tried on the variable frame rate cases. Yes.
Wow, awesome. Okay, here's one that I think might be a fun one. Seriously, why bother with AI and deep learning? Why not just improve the existing metrics for your use cases?
That's a thought we've been dabbling with for a long time, right? In the industry, maybe about closer to 30, 40 years now, trying to look for the holy grail with like the existing metrics kind of a case. Some of these problems are non-solvable with existing. PSNR, for the longest time we know, is problematic, right? But still, we keep using PSNR because of lack of anything better to say the least, right? So we can tune and try multiple different things for different use cases, and UGC, we have seen it grow in the last 5 to 10 years. Social sharing has become substantially a lot more than your traditional broadcast-based video, and so reference-based metrics in general have become slightly non-accurate for certain applications in general. And we have tried. There's been a lot of attempts at tuning some of these existing metrics. We, in the sense of like all of us, right? The community, the quality community, has been looking at it for like a good part of 20 plus years. And tuning cannot get better after a particular point. Not necessarily saying AI is the solution here or the deep learning, but it seems to perform better than tuning the existing metrics at this point. So.
Yeah, UGC video quality assessment is a relatively new research topic, and every year there are still many papers in this area. And why it's different from traditional video quality assessment, mainly because the diversity in the content and in original quality. And PSR, SSM, VMF, they are very good metric, but they are not designed for UGC, especially when the original quality is not pristine. So yeah, and in our application, we also find the content play an important role when we assess video quality. That's why we want to utilize the machine learning techniques to improve the accuracy of the metric.
Got it. All right. We have a lot of questions coming in. I'll leave with this last one. Sorry to everyone whose questions I didn't get to. And I think just for fairness, we're going to ask this one because we asked it in the last one. I think it's a great conversation starter as well. As we talked with Pranav, we want to ask you the same question, right? So where do you see the state of the art in quality measurement going long term?
Yeah, I can take that question. So we think like assess video quality as a human expert may be the future of this area, right? We should not just focus on the signal level, the like pixel level signals. We should understand the video quality as a entire thing from the semantic level to the low pixel level. And also there are some challenging, like maybe the score, maybe now we think 1080p or 2K, 4K quality is perfect, but maybe 5 years later, 8K or 16K, we think that is the expectation of the human. So how to handle that increasing human expectation and reflect that in our quality metric is a challenging. Right? And how to build the personalized quality assessment score is also an interesting topic. Yeah.
Maybe you can briefly add to that. I think in the long term, there might be a sense of more correlation to what the subjects feel. I would probably model it around JNDs, right? If the humans can observe it, that's a valid change. Like a metric giving you like a half a dB improvement, and if that does not reflect on like people's perception, like people can't understand the difference, then it's probably difficult to say that it is an actual improvement, right? So I would model the metrics around like what humans feel is a noticeable difference. Just like audio, right? You have the audio knob which goes from like 0 to 10 or 0 to 20. You go from 15 to 16, the volume increases. You have no idea what 15 is or 16 is or what scale it is at, but you actually hear a difference, right? I expect a similar thing from video as well, where you see the difference with each of those metric differences. So.
I love that analogy. I think we are a little bit over, but thank you so much. We have so many great questions. It seems like the audience really likes generally this topic of discussion. The past 2 talks have had a lot of interest. So if you guys have time afterwards, please hop over to the live stream and you can answer some of them in line if you'd like to or have time. But yeah, I think with that, we'll transition over to our next speaker, who is Ronald from 2 Orioles, to talk about scaling your encoding backend with the Eve encoding framework.